Welcome, everyone, to this afternoon session of the PhD Symposium, session 1B. You have three persons chairing you this afternoon, and we just like a brief introduction. My name is Nour Olsen. I'm the current president of FIB. I'm not a professor, as it says here. I'm a structural designer, and I come from Norway. So please, Bruno, do you want to present yourself?
Yes, I am Bruno Godard, the deputy head of the Materials and Structures Department at the Université Gustave Eiffel, and I am also the president of the French Association of Civil Engineering, which is representative of FIB in France.
Okay, thank you. And Graham?
Hello, my name's Graham Webb. I'm a bridge engineer I work for WSP in London in the UK, and I'm a member of the FIB Young Members Group and the UK FIB delegation.
Thank you. And then we are ready to start with Abdel, dimensioning approach of partially pre-stressed concrete beams, optimization of simply supported beams.
First of all, I would like to present myself. This is Nadim Abdel Nour. I'm a PhD student at the Université Clermont-Auvergne, Clermont-Ferrand à Paris. First of all, I would like to thank the chairman of this session and all the attendees. I'm here to present my article, Dimensioning Approach of Partially Prestressed Concrete Beams, Optimization of T-shaped Section with Heels. Okay, I will start my presentation. First of all, I would like to remind the principle of prestressing. It was introduced by Eugène Freycinet in 1928. It is used to compensate the small resistance of concrete under tension by creating an initial compression force using the prestressing cable. We have two types of prestressing: full prestressing, in which we maintain the concrete in a full compression state under extreme service loads; partial prestressing, in which we are allowing tension stresses and limiting cracking in the concrete sections. The main objectives of this article are: one, develop a new approach for dimensioning of prestressed concrete section. This new approach is applicable for both full and partial prestressing. It combines all service limit states and ultimate checks. It represents the permissible domain and formulate the former condition known in French code comme la condition de coffrage. In the second part, this new method is implemented in an optimization procedure based on genetic algorithm with the total cost as an objective function. And at the end, the numerical examples showing the effectiveness and performance of this method will be presented. Conventional design method. First of all, I would like to start by presenting what is usually done in conventional design method. Usually, for each service limit state, we start by computing the values of P critical and P over critical, known in French code, la valeur de P sous critique et la valeur de P sur critique, based on stress limitation and cover conditions. And then the higher values of those two P's is considered for the design. As for the former condition, known comme la condition de coffrage, it results from the upper and lower stress constraint based on which the minimum needed concrete section for serviceability checks is deduced. Now the new pivot method we're presenting. In this method, the principle of this method, the prestressing force P is considered as an exterior force acting on our section, and the crack width is replaced by a limitation on the stress in the passive reinforcement based on the provisions of the Eurocode. And since we're dealing with T sections with heels, the width B of this section varies linearly along the height of the section. Therefore, the mechanical properties can be obtained by successive integration. We profited from this property for the analytical formulation of our new approach. The main equation of this new approach are obtained from the basic equilibrium equations, which are the axial force and the bending moment, based on which a general polynomial function of the neutral axis position was obtained. This general polynomial equation f of x can be used for both full and partial prestressing, with the only difference that when it is used in full prestressing, we have a fictitious position of the neutral axis since it will be located outside our section, whereas when it will be used in partial prestressing, we have a real position of our neutral axis since it will be located inside our section. Now, this new pivot rule applied for fully prestressed section. First of all, we start by finding the neutral axis position by solving the main polynomial equation f of x equals to 0. The well-known stress expressions on extreme fibers for full prestressed concrete sections are found. The permissible domain is drawn by expressing the stress limitation in the plane P M star. This domain is delimited by 4 lines that are parallel to each other 2 by 2 and forming a parallelogram. The following pivot rule representation shows the evolution of the stress diagram by moving along the contour of the permissible domain. For example, when we are moving along line D3, as if we are rotating around pivot 3, and the stress sigma 3 is reached. When we reach the intersection of 2 consecutive lines of the contour of our permissible domain, 2 stress limitations are reached simultaneously. In addition, the known values of Pmin and Pmax can be obtained graphically and analytically. And finally, we can see the clear representation for the allowable limits of P inside the permissible domain. Now, if this new pivot rule is applied in partially prestressed concrete section, the same polynomial equation f of x can also be used in order to find the values of P critical and P over critical. The same pivot rules applies, with the only difference that the lower stress limitation sigma 4 will be replaced by a stress limitation on the passive reinforcement AST. For the domain extension, we can see here clearly the domain extension. The extended parts of our domain consist of 2 curves that represents pivot 2b and pivot 4b. The intersection between the pivot 2 and the pivot 2b, it is clearly the limit between cracked and uncracked section. We also have a significant gain in the value of Pmin, since the limit D4 of our permissible domain is replaced by pivot 4b, by the curve pivot 4b that is shifted further up. Now, for the former condition, ou bien la condition de coffrage qui est bien connue dans les normes françaises comme ça, in this former condition, actually this former condition is expressed or is represented in the plane delta MP for both full and partially prestressed and partially prestressed section. It is expressed independently from the values of P and E0. This condition is considered to be verified if the difference between the maximum and minimum exterior applied moments is less than the maximum delta M value. We can clearly see here the extension of the former condition due to the partial prestressing. And in addition, we have again in the former condition if for values of V over V prime less than 1. Finally, for the ultimate bending verification, and since in our new approach, the value of P is presented in terms of permissible range of value, we try to follow the same principle here, and the minimum value of PU for which the section is verified under ultimate loads was found. In case this value of PU is less than P service, this means that the ultimate check is verified. Some of the advantages of this method can be easily implemented in optimization algorithm. It coherently combines all service limit states in one formula. we have the same formulation for both full and partial prestressing. It allowed the formulation of the former condition in partial prestressing, which is something new. We have a clear representation of the permissible domain with the range of value of the permissible values between Pmin and Pmax, and a good importance should be accorded to Pmax, since it might control the design in some of the serviceability cases, in some of the service combinations. And finally, it allowed the designer to visualize the solution obtained in conventional design method with respect to the limits of the permissible domain. Now we move to the optimization part. An optimization procedure was implemented based on genetic algorithm with a penalized cost objective function with geometrical and flexural constraints. The design variables are the geometrical dimensions of the sections, the percentage of passive reinforcement, and the tendon configuration. When it comes to the optimization methodology, and since we are using a genetic algorithm, the following was followed. First of all, an initial population was generated randomly. For each individual, when we say individual, this means for each couple VH generated of this population, the dimensions or the optimal dimension of the heels were found based on the computed p-value and on the tendon configurations that were introduced automatically in our Scilab program. This calculation is repeated for each individual of the first population. At the end of the first iteration, all the objective functions are evaluated and the genetic operators are used in order to generate a second population and move to the second iteration. This iteration process shall continue until reaching the stop criteria and the optimal solution is obtained. A numerical example, the presented optimization procedure was used for a prestressed concrete 3-lane bridge. The calculations were performed on the edge beam, which is subjected to the most severe loading based on a transversal load distribution that was performed following Courbon's method for any transversal load distribution. And a parametric calculation was carried on for several span lengths in order to study the effect of the following parameters: the formwork ratio, the ultimate bending verification, the steel reinforcement ratio, and the heel dimension. When we say a formwork ratio equal to 1, this means that the corresponding constraint is equal to 1 and it is saturated. This means this constraint is controlling the design. And this applies for the ultimate ratio, for the formwork ratio, for the shear ratio. This is the definition of a ratio. In the first plot here, we're seeing the ratio, the formwork ratio and the ultimate ratio versus the span length. It's clear that for spans less than 40 meters, the formwork condition controls the design, whereas for spans bigger than 40 meters, the ultimate check controls the design. In the second plot, we're seeing the heel area versus the number of cables. It is clear that for a number of cable equals to 3, the heel area is null. The heel area started to increase with the increase of the number of cables. This means that the heel area or the heel size has no added value to the design capacity of the section. It is only used for the placement of the cables. Now we move to the effect of the steel reinforcement ratio. First of all, we will study its effect in full prestressing. We are showing in the first plot the beam depth versus the steel reinforcement ratio. It is crystal clear that we have a gradual decrease in beam depth with the increase of steel reinforcement ratio. This is due to the fact that the ultimate check are controlling our design. In the second plot, we're showing the effect of the steel reinforcement in partial prestressing. We're showing the value of the prestress force P, of the obtained prestressing force P versus the steel reinforcement ratio. We obtained a clear reduction in the prestress force P for an increase in steel reinforcement from 0.2% to 1%. Then a comparison between full and partial prestressing was performed. This comparison was performed for same span lengths and same steel reinforcement ratios. we obtained a significant decrease in prestressing force between full and partial prestressing. Also, we had a decrease in the formwork ratio. This means that the constraint wasn't saturated in partial prestressing. And finally, a sensitivity cost analysis was performed, a sensitivity for the cost of the concrete and the active reinforcement was performed. It was clear that the optimum solution is directly affected by the unit cost. And finally, we can say that, that this optimization procedure or the objective function related to this optimization procedure can be easily modified based on the designer's objective, which means that if the designer chooses to minimize, for example, the prestressing forces, the concrete section, the passive reinforcement, this can be done easily. The objective function can be modified easily as opposed to conventional methods for dimensioning. That's it. Thank you very much for your attention.
Thank you very much. That was a very, very clear presentation. I understood it, I think, most of it.
Thank you.
Are there any comments or questions from the audience?
Bruno Godard, yes, I have two questions, maybe. And if you show the slide 17,
yes,
in your optimization with the genetic algorithm,
yes,
it seems that the ratio of steel reinforcement bars has not been considered as a flexural constraint.
No.
And can you explain why?
No, actually, I tried to program my algorithm in a similar way to what designers do in practical life, which means for a certain specific percentage of steel reinforcement, I am running a certain optimization calculations. This means that my calculations will be repeated for several percentage of steel reinforcement. This means that for each percentage of reinforcement, I ensured that the needed rebars had enough place to be placed inside the heel of my section. But the steel reinforcement was not a design variable. It was something that was specified at the beginning of each iteration.
Okay, but it could be considered also as a variable.
Yes. I
Okay.
didn't say no. Yes.
Okay, and my second question is about the fatigue limit state. I am talking about the fatigue of steel reinforcement and fatigue of steel prestressing. Have you an idea how to take into account these rules on fatigue in your procedure?
Yes, actually, they can be implemented. They can be implemented in our calculations.
Yes, but it's not done for the moment.
No. It's not done for the moment. It's not done for the moment.
Okay. Thank you.
You're welcome.
Okay. Any other questions? I have one question. After reading your paper, I got the impression that this tool of yours is also thought used for conceptual design.
Yes.
Yes. Okay. And as such, it's very valuable. And if you take up your page 22 from your presentation.
22, yes.
So my question is, at the bottom there, you say objective function, easily modified, based, etc.
Yes.
And so my question is, let's say that you are not optimizing on the cost of the beam itself, but something else. For example, if you have limited crane facilities, or could you then just put that into your model and optimize on that, for example?
Yes, actually, if I had a limited crane facility, for example, my concern is to limit the weight of my beam, if I got you right.
Yes, yes.
If this is the objective, is to limit the weight of my beam, I can easily modify my objective function. It will be the area of my beam or the total section of my beam. Once my objective function is modified, I can modify my algorithm. So I will be minimizing the weight of my beam.
Yes,
This
okay.
means I might need to add extra rebars, I might need to add extra cables, extra active reinforcement, but in this specific model I'll be doing, my purpose is to minimize the weight of my section.
Yes. Well, that's good, because so you end up with a little bit more expensive beam, but maybe less expensive crane, for example.
Exactly.
Yeah.
Exactly. This is the point.
Well, that's good. I think your approach in the case of conceptual design is very important, because conceptual design often have very many unknowns, and it may be a little bit difficult to arrive at what exactly you should optimize on.
Exactly.
So I think tools like this is valuable.
Can I just follow off to that? What do you think's the most kind of the best use for this? Do you see it being useful when you're at a conceptual design stage, or is it going to be more useful for optimizing at the later design when you've closed out most of your design decisions?
Actually, I can say it can be used in both cases. Since using it at early stages is efficient, since we will have an idea of the section that we might obtain in the final design, and since it is not the way the analytical procedure is formulated is not something complicated, though it can be used even at early stages. We don't have any complicated calculations to say that we will leave such complicated calculations for advanced stages of the project. So I can easily say that it can be used for at early stages and at final design stages.
Okay, and how long does the optimization take to run?
Actually, it's a question of 1 or 2 minutes on Scilab. If you know Scilab, it's similar to MATLAB. It's 1 or 2 minutes, not more. Not more.
Yes, I have another question. Is
Yes.
to ask in which order do you manage the checking of ultimate limit state and service limit state?
Actually, if we go to conventional design method, in conventional design method, we start by checking our section at service limit states. Then we verify our section for ultimate checks. This is what is usually done.
Yes.
Here, our optimization procedure is a bit similar to what is usually done in the conventional procedure. We start by finding the value of the prestressing force that is needed. After that, we choose the heel dimension. We found the heel dimension based on a specific tendon configurations that were introduced in table forms in our algorithm. Then we perform the ultimate check verification. But it turned out that in all optimal solutions, the ultimate check verification is controlling the design. This doesn't mean that we are performing the ultimate check design at before the service check. We're following the same steps. We're at the first step, we're doing the serviceability checks. We're finding the force P. Then we're performing the ultimate checks. But it turned out that the ultimate checks are controlling the design, even though they are not performed before the service checks.
Okay, and your optimization is working on both aspects? Or
yes, for sure. Actually, what we did, we created what I called ratio. we have a ratio for the values of P, we have a ratio for the former condition, we have a ratio for the ultimate verification, we have a ratio for the shear verification, a ratio that has a value of 1. This means that the constraint is saturated and it is controlling the design. So all those verifications, all those checks are included in the design. Actually, in the presentation, in this table, I'm going back. When I mentioned here, we have the flexural constraint. The flexural constraint here in this slide include the minimum prestressing force, the maximum prestressing force, the former condition, the ultimate bending check, and the shear verification. All those constraints are took into consideration in our optimization algorithm, in addition to the geometrical constraints.
Yes. And for the shear verification, it's at ultimate limit state?
Actually, for the shear verification, as per the provision of Eurocode, it is permitted to use annex QQ. In this annex...
okay. You use annex Q. Yeah.
Yes, exactly.
Okay, okay. Thank you.
Thank you very much. That was a nice presentation. Thank you.
Thank you.